For 70 years, we have spent, billions of dollars building these massive underground detectors, basically looking for a ghost.
Yeah, a ghost we call the dark matter particle.
Right. Because we are absolutely certain that something invisible is holding spinning galaxies together, preventing them from just ripping apart.
Exactly. And at the same time, we know something else is pushing the entire universe apart faster and faster, which we call dark energy.
So generation after generation of physicists have searched for the hidden wires, like the physical particles making all of this happen. And despite all that time, the money, the brilliant engineering, we haven't found a single one.
Not one.
So for today's deep dive, we're asking a pretty massive question. What if we haven't found the wires because we've been looking for a prop, when we really should have been looking at the stage itself?
That is the profound shift in perspective we are examining today. Because when we look at standard cosmology, the assumption is always that if something is being pushed or pulled, a physical object or particle must be responsible.
Right, which makes intuitive sense to us.
It does. But we are diving into a fascinating 2026 paper by independent researcher Fake Sumik. It's titled Geometric Phase Transition in the Dark Sector.
And the mission of this deep dive is to explore the main argument of this paper, which is that dark matter and dark energy aren't two different things. And this is the wild part, they aren't particles at all.
No, they're not. They're the exact same thing, just different states of the vacuum of space itself, entirely dictated by how much that space is stretching.
Okay, let's unpack this. Because to really understand why this paper is such a radical departure, we need to look at the blueprint we've been using up until now.
Right, the lambda CDM model.
Exactly.
And, the lambda CDM model does an exceptional job predicting the broad strokes of the universe. Lambda represents dark energy, which drives cosmic expansion, and CDM stands for cold, dark matter.
And cold just means these hypothetical particles move slowly enough that they can clump together under gravity, right? Like an invisible scaffolding that galaxies are built on.
Precisely. But the model is starting to crack under the weight of actual observation.
Yeah, the paper specifically calls out the nature problem, which is what we just touched on. The whole model relies on a particle that seemingly doesn't exist. But there's a second flaw, too, the cosmic coincidence problem.
Right. In our current standard model, dark matter and dark energy are completely unrelated phenomena. I mean, one pulls things together and the other pushes the universe apart.
Total opposites.
Exactly. Yet when we calculate their current densities in the universe right now, they are in this highly delicate tug of war. They are remarkably comparable in strength.
Which is weird, right? If they have absolutely nothing to do with each other.
It's incredibly weird. It requires an absurd level of fine-tuning for them to be so perfectly balanced in our specific present moment in cosmic history.
It's like finding out your neighbor's car and, I don't know, a random asteroid in the asteroid belt happened to weigh the exact same amount to the gram on a random Tuesday. The math technically works, but it feels too deeply weird to just be a mere coincidence.
What's fascinating here is how Sumik's model actually resolves this. He completely strips away the need for two separate entities.
By proposing they're just manifestations of the same underlying quantum vacuum energy. The only difference is the phase state.
Yes.
The paper uses this brilliantly simple analogy to visualize it. Think about water, right? H2O. You have ice, liquid water, and vapor.
They behave completely differently. I mean, ice is rigid, but vapor expands to fill a room.
Exactly. But at a molecular level, it's all the exact same stuff. The only reason it transitions from one behavior to another is because of the local temperature and pressure.
And in Sumik's framework, the vacuum of space itself is capable of existing in different phases, just like water.
But obviously, we aren't talking about temperature and pressure freezing the vacuum.
Oh, no. Instead of temperature or pressure triggering the change, the vacuum transitions based on geometric strain. So when the space-time metric is placed under a specific level of tension, it behaves in a matter-like state, which is what we observe as dark matter. And when that tension relaxes, it behaves in an energy-like state, which we observe as dark energy.
Wait, I need to push back on this a bit, because it feels like a logical leap to wrap my head around. If dark matter is just stretched space, how does it actually have mass? Like, how can something that isn't a physical particle exert a gravitational pull on a massive star?
That's a great question. It comes down to mass-energy equivalence. Energy and mass are essentially two sides of the same coin. They both curve spacetime.
Okay, EMC2 kind of stuff.
Exactly. To understand how vacuum strain determines whether space behaves as dark matter or energy, you have to stop thinking of the vacuum as just pure nothingness.
Right, it's not just an empty box.
No, it is a physical medium, and it has tensile strength. When the fabric of spacetime stretches, that tensile strain, which sumic represents with the Greek letter sigma, it increases.
Okay, so sigma is the amount of stretch.
Right. And when that strain exceeds a critical threshold, which he calls sigma critical, the vacuum undergoes a phase transition to store that energy more efficiently.
So it condenses.
Yes, it condenses into a high-density state. That intense localization of vacuum energy curves the surrounding space, and that curvature creates the exact gravitational effect we've been attributing to dark matter.
Oh, wow. So under the old model, we thought a dark matter halo around the Milky Way was this giant cloud of invisible particles trapped there by gravity.
Right, like bees swarming a hive.
But under this paper's framework, what they call the prisoner condition, that halo is not a cloud of stuff. It is physically confined by the geometry of the space itself.
Exactly. The dark matter only exists because the geometric conditions in that specific region demand it. Gravity isn't what keeps the dark matter trapped around the galaxy. Gravity is merely the symptom of the vacuum being in that condensed, highly strained state.
It makes me think of a thick rubber band. When it's relaxed, it's thick and, let's say, blue. But when you pull it incredibly tight, putting it under extreme tensile strain, it sends out and turns bright red.
That's a perfect analogy.
The red color isn't some new material you painted onto the rubber band. It is just a property of the rubber band being under high tension. If you let it go, it returns to blue.
That captures the mechanism perfectly. And we can actually extend that rubber band analogy to explain a really vital mathematical component of this theory: hysteresis.
Hysteresis, or geometric memory, right?
Yeah.
Because if the vacuum transitions at a specific threshold, you'd assume that the second the tension drops, even slightly below that line, it would instantly flicker back to dark energy.
But it doesn't.
Right.
Think about your rubber band. If you pull it just tight enough to turn it red, you can't make it turn blue again by relaxing your grip a single millimeter.
Oh, I see. You have to let it go almost completely slack.
Exactly. Once the vacuum enters the highly strained dark matter phase, it develops a kind of memory of that state. To transition back to dark energy, the local strain must drop to a significantly lower threshold, which the paper calls sigma decay.
And that memory effect is what keeps the dark matter halos stable over billions of years. Without it, the halos would just constantly boil away every time a random star moved and slightly altered the local gravity.
Right. And it also elegantly solves a major observational mystery regarding how galaxies form. You see, when we look at normal baryonic matter, the stars and the gas, it spins, it collides with itself, loses kinetic energy, and eventually flattens into a rotating disk.
Which is why the Milky Way looks like a flat pinwheel.
Exactly. But dark matter halos are spherical. They never collapse.
And in the old particle model, physicists had to invent all these complex rules for why dark matter particles somehow never bump into each other, right?
Right, they had to be collisionless. But in this geometric model, the answer is trivial. They don't collide because there's nothing to collide. A property of spacetime cannot collapse into a disk. It simply exists wherever the strain conditions are met.
Here's where it gets really interesting, though. If a highly stretched vacuum is what creates dark matter, what in the universe is doing the stretching? I mean, a perfectly static, quiet universe wouldn't have any strain.
No, it wouldn't. The paper introduces what it calls a two-phase pump that acts as the engine for this entire process.
Okay, so dynamic structures in the universe are mechanically inducing this strain. Let's talk about the first phase, the primordial pump.
Right. This operated in the extreme environment of the early universe, long before stars even existed.
We're talking about the time when the universe was just this remarkably dense, blindingly hot soup of plasma.
Yes. During that radiation-dominated era, the universe was filled with massive acoustic waves, literally giant pressure waves or sound ripples, propagating through the primordial plasma. They're known as baryon acoustic oscillations.
And as these massive sound waves rippled outward, they created peaks of extreme compression and then troughs of profound stretching.
Exactly. And that stretching induced severe tensile strain on the local space-time metric.
But the universe was expanding and cooling at the same time. Eventually, it cooled enough that the plasma neutralized and the universe became transparent.
Right, the moment of recombination. And at that precise moment, the acoustic waves effectively stopped. But the geometric strain they had inflicted on the space-time fabric did not vanish. It froze into the vacuum.
Wait, it just froze there.
It did. Wherever the strain from those final sound waves exceeded the sigma critical threshold, the vacuum condensed into the very first patches of dark matter.
That is wild. The first dark matter was literally a fossilized echo of the Big Bang's sound waves. It essentially poured the foundation, creating the initial gravitational wells where galaxies would later form.
And this naturally accounts for a massive piece of observational data that the standard model really struggles with. When we map the distribution of dark matter in the modern universe, it clusters perfectly at a scale of roughly 150 megaparsecs.
And to put that in perspective for you listening, 150 megaparsecs is almost 500 million light years across.
It's massive. And the standard model has to basically bolt on extra physics to explain why dark matter clusters at that specific massive scale. But Sumik's model predicts it naturally because those giant sound waves directly dictated where the dark matter could form.
So the primordial pump created the seeds.
Yeah,
But as the universe continued to expand over billions of years, that fossilized background strain would naturally stretch out and dilute.
it would, yeah.
So if that was the end of the process, the tension would have eventually dropped, and all the dark matter would have reverted to dark energy. We need a second phase to keep the tension up.
And that second phase arrived when baryonic matter, the gas and dust, fell into those primordial dark matter wells and ignited into galaxies.
Wow.
The moment galaxies formed, they introduced a localized, ongoing source of mechanical strain, the galactic pump.
I love this part. Think of the galactic pump like an enormous cosmic blender. Because galaxies are incredibly messy, right? They don't just sit perfectly still in space. They spin violently, they wobble, they have satellite dwarfs, galaxies, constantly orbiting them and pulling with tidal force.
It could crash into one another.
Exactly.
Every single star, gas cloud, and massive black hole in that system acts as a mechanical paddle. As they move through the halo, they are physically kneading the space-time vacuum, creating intense localized tension that continuously churns dark energy into fresh dark matter.
So the chaotic asymmetrical motion of a galaxy is actively sustaining its own dark matter halo.
Yes.
But if galaxies are constantly churning the vacuum locally, how does this process relate to the fact that the entire universe is pushing itself apart?
Yeah.
The paper outlines a closed-loop cosmic ecosystem that ties the whole thing together.
It does. Let's trace the life cycle of this energy. As cosmic expansion drives the universe apart, it severely stretches the massive empty voids between the galaxy clusters.
Okay, so the sheer expansion increases the tensile strain within those empty regions.
Right. The fabric in the middle of nowhere is being pulled incredibly tight. And when the strain in those empty voids crosses that critical threshold, the dark energy sitting in the void condenses into brand new dark matter.
And because this new dark matter possesses severe localized energy density, it curves space-time. It has a gravitational pull, therefore, it begins to flow toward the deepest gravitational wells nearby.
It flows toward the galaxies.
But it doesn't just stack up around the galaxy infinitely, right?
No, it encounters what Sumik defines as the unstable edge of the galactic halo. Remember your blender analogy. The outer edges of a spinning, wobbling galaxy are highly turbulent.
Right.
As the fresh dark matter flows into this boundary, it gets subjected to the complex orbital dynamics of the galaxy's outer rim. The sheer mechanical rotation locally compresses the space, causing the tensile strain to wildly fluctuate.
And when that orbital compression causes the local tension to drop below the geometric memory threshold, that sigma decay limit we talked about earlier, the dark matter can no longer hold its condensed form.
It decays. It instantly relaxes back into the low-density dark energy state. And, as we know, phase transitions release energy.
So when that dark matter decays back into dark energy, it releases an expansion pressure into the local vacuum,
Exactly.
and that released pressure pushes outward, contributing to the cosmic expansion, which then stretches the empty voids even further, which creates more dark matter, which flows back to the galaxies to be ground up and decayed. It is a completely self-sustaining engine.
If we connect this to the bigger picture, it answers the cosmic coincidence problem beautifully. We are not living in a highly fine-tuned accident.
We just happen to live in a specific era.
Right. We simply live in an epoch where there is enough galactic structure acting as paddles to run the pumps efficiently, but the universe hasn't expanded so far that the voids are too distant to feed the galaxies.
So the densities of dark matter and dark energy are comparable right now because they are part of a self-regulating equilibrium. One literally fuels the creation of the other.
Exactly.
This entire framework is stunningly elegant. But, beauty doesn't make a theory true. We need testable proof. How do we verify if a geometric phase transition is actually happening out there?
Well, Sumik's paper is actually very rigorous in providing falsifiable predictions. Predictions that directly conflict with the lambda CDM model. These are measurable anomalies we can look for right now.
Let's go through them. The first prediction focuses on void thermodynamics. In standard cosmology, the vast empty voids between galaxies are essentially just dead space.
But under this geometric theory, those voids are highly active factories where dark energy is condensing into dark matter. And thermodynamics dictates that a phase transition of that magnitude cannot be perfectly efficient. It must release a faint thermal signature.
So the paper predicts that these cosmic voids should emit a diffuse low-energy radiation background, making them ever so slightly warmer than the standard model allows.
Exactly. And we can actually search for this heat signature by deeply analyzing the cosmic infrared background.
Okay, what about the halos themselves? If the voids are the factories, the halos are the incinerators, right? We talked about that unstable edge where dark matter decays. If I'm flying a ship out of the Milky Way, standard physics says the dark matter will just gradually thin out into nothingness.
But Sumik's model predicts you would hit a sharp, highly turbulent boundary. Dark matter halos should have distinct, fuzzy edges, corresponding precisely to the mathematical surface where the strain drops below the decay threshold.
And the thickness of this boundary would vary, wouldn't it?
It would. A quiet, isolated spiral galaxy might have a relatively clean edge, but a massive cluster of colliding galaxies with highly chaotic orbital dynamics would feature a thick, violently boiling boundary.
We could actually map those boiling edges, couldn't we?
We could by utilizing weak gravitational lensing. You see, instruments measure how light from background galaxies bends as it passes through a foreground dark matter halo.
So if the edge is turbulent and decaying, the way the light bends will carry specific chaotic signatures rather than just a smooth gradient.
Precisely.
There is also the transition epoch prediction, which is super interesting. If the universe switched from the primordial pump to the galactic pump, we should see that handover in the observational data.
We can look back in time by observing highly redshifted light. Around a redshift of 1 to 2, which corresponds to roughly 8 to 10 billion years ago, galaxy mergers and interactions began to ramp up significantly.
Okay.
So we should observe a distinct shift in the efficiency of dark matter halo formation relative to the visible stars during that exact epoch.
This raises an important question about how we allocate our resources.
Yeah.
Because we have next-generation observatories coming online right now.
We do. The Euclid Space Telescope, the Dark Energy Spectroscopic Instrument, the Rubin Observatory, and the upcoming LUMEN gravitational wave detector.
Wait, gravitational waves?
Yes. Sumik predicts that the mechanical churning of the galactic pump will generate a very specific, low-frequency stochastic background of gravitational waves.
Oh, wow. We possess the exact tools necessary to test these anomalies, instead of just looking for ghost particles in underground labs.
So what does this all mean for us? For nearly a century, we have treated the invisible forces of the cosmos as a search for missing puzzle pieces, right? We've been looking for physical particles to place onto the board.
Right.
But if fake Sumik's framework holds true, dark matter isn't a piece on the board. It is the physical tension of the board itself. We have fundamentally misunderstood the nature of the vacuum, treating it as empty space when it is a dynamic, strain-responsive medium.
It really demonstrates how our terrestrial intuition, built on interacting with physical objects, can blind us to the true mechanics of the cosmos.
Yeah.
The universe does not owe us a particle just because our equations demand a source of mass.
It changes everything about how we look at a spinning galaxy.
It does. And there is a final implication in this paper that really warrants deeper consideration. If the dark sector, which makes up 95% of our universe, is purely a manifestation of geometric strain.
It forces us to reconsider the fundamental nature of the remaining 5%.
You mean the visible matter, the stars, the planets, you and me.
Exactly. We currently treat gravity as a fundamental force exerted by matter. But if the immense gravitational pull of a dark matter halo is simply the byproduct of the vacuum trying to efficiently store its own geometric tension, perhaps our understanding of gravity itself is inverted.
Wait, inverted how?
What if gravity isn't a force pulling things together at all, but merely the observable symptom of the universe constantly trying to relax its own internal tension? If the invisible stage is defined entirely by geometry, perhaps the visible props are too. Are we just another wrinkle in the geometric fabric?
We started out looking for the hidden wires, pulling the universe together. But maybe the real trick is realizing there are no wires, no props, and no distinct actors. There was only the canvas, stretching and folding against itself. Definitely something to keep in mind the next time you look up at the night sky.